In the previous lecture, we learned the method of Lagrange multiplier. We use this method when we want to minimize or maximize a function that is subject to a constraint. And the method is to write out 4 equations when we have a function of 3 variables. The first 3 equations is the gradient of the function equals to some constant, lambda, times the gradient of the constraint. And the 4th equation is the constraint itself. Now in this lecture, we are going to look at 2 examples using the method of Lagrange multipliers. Here's the first example. This problem is actually the same problem as example 3 in lecture 84. That is, we want to maximize the volume of a rectangular box without the lid, given that the box is made from 12 meters square of cardboard. And remember that from lecture 84, we solved this problem by writing out the height of the box, c, as a function of x and y. Then we substitute the z back to the volume function. Then the volume function is now a function of 2 variables only. Then we find the critical points of the function and substitute the critical points back to the volume function. But in this lecture, we are going to use the method of Lagrange multipliers. Then what would be the function that we want to maximize and the constraint to the function? So the function will simply be v equals to x, y, and z. And we'll leave the function as a function of 3 variables. We are not going to substitute the z back to this function. And the constraint is that the surface area of the box is 12 meters squared. So here's the translation of the problem in terms of the function that we want to maximize and the constraint. We want to maximize the volume function v equals to x, y, z, subject to the constraint g of x, y, and z that equals to the surface area 2 times xz plus 2 times yz plus xy, and the surface area is a constant, so this constraint equals to 12. Then using the method that we learned in the previous lecture, I'm going to write out 4 equations. The first 3 is the gradient of the volume function equals to the Lagrange multiplier, lambda, times the gradient of the constraint, del of g. And we also have an equation for the constraint. So g of x, y, and z equals to the constant 12. Then from here, we can write out 4 equations. The first 3 are the components of the first equation on the left. The x component would be v sub x, the derivative of the volume function with respect to x, so that's y times c, equals lambda times g sub x, the partial derivative of the constraint with respect to x. That would be 2 times c plus y. And we do the same thing for the y and the z components. So the second equation would be x times c equals lambda times 2 times c plus x. And the z component, x times y equals lambda times 2 times x plus 2 times y. And the 4th equation is simply the constraint. So 2 times xz plus 2 times yz plus x times y and equals to the constant 12. Let's name these 4 equations as equation 1 to 4. Now we have 4 equations and 4 unknowns. The unknowns are x, y, z, and the Lagrange multiplier, lambda. There's no specific way on how to solve for these 4 unknowns, but when we have 4 equations with 4 unknowns, then we should be able to solve for this system of equations. Note that the left-hand side of the first 3 equations is always product of 2 variables. So now to solve for this system of equation, I'm going to make their left-hand side the same. That means I'm going to multiply x to the first equation and multiply y to the second equation and multiply z to the third equation. Now I get to these 3 equations, and I'll call them equation 5 to 7. And these 3 equations have the same left-hand side. That means I can equate their right-hand side, and note that they all have a lambda in the right-hand side. If lambda equals to 0, then the right-hand side of equation 5 to 7 will simply be 0, and that will satisfy the system of equations. However, lambda equals to 0 cannot be a solution, because we can note from equation 1 to 3, if lambda is 0, that means the left-hand side, y times c, x times c, x times y would equal to 0. But if these three terms equal to 0, then equation 4 means 0 plus 0 plus 0 equals to 12, which is not consistent. So lambda equals to 0 cannot be a solution. So instead, when we equate the left-hand side of equation 5 to 7, that means we are equating the terms in bracket. So this equals to this, which equals to this. Let's start with the first two equations. So let equation 5 equals to equation 6. Then we get 2 times xc plus xy equals to 2 times yc plus xy. I can cancel out the plus xy and also the 2, the constant. So I get from here x equals to y provided c does not equal to 0. And I can do the same thing for equation 6 and equation 7. So let equation 6 equals to equation 7. That means we're equating the terms in bracket. And I get 2 times yc plus xy equals 2 times xc plus 2 times yc. I can cancel out the 2 times yc. Then I get y equals to 2c provided x does not equal to 0. Now I can use the last equation that I haven't used yet, which is equation 4. So we substitute what we just found, that is x equals to y, which equals to 2c, into our equation 4. Then we get 4 times c squared plus 4 times c squared plus 4 times c squared equals to 12. That means c equals to 1. And since x equals to y, and that equals to 2c, so that means x and y both equal to 2. And that is the critical point of the volume function, a function of 3 variables. So what's the conclusion? Given that the surface area of the open-lid rectangle box is 12 meters squared, then the maximum volume of the box has dimensions of 2 meters times 2 meters times 1 meters of height. And note that that is the same answer as we found in lecture 84. Now let's look at the second example. Let's find the extreme values of the function x squared plus 2 times y squared on the circle x squared plus y squared equals to 1. Here the function is only a function of 2 variables, and the constraint is the circle with radius 1. Using the method of Lagrange multiplier, we can write out 3 equations with 3 unknowns, x, y, and lambda. The equations are the gradient of the function f equals to the Lagrange multiplier, lambda, times the gradient of the constraint, g. And the last equation is the constraint, g of x and y equals to the constant 1. So this gives us 3 equations. First 2 equations are the x and the y components of the first equation on the left-hand side. That is f sub x, which is 2x, equals to lambda times g sub x, that is 2x. Then the y component, f sub y, we get 4y and equals to lambda times g sub y, that is 2y. And the third equation, the constraint, is x squared plus y squared equals to 1. And let's call them equations 1 to 3. From the first equation, we note that there's the 2x on both sides. So x and lambda satisfy this equation. If x equals to 0, then we get 0 on both sides. Or lambda equals to 1. So from the first equation, we have 2 possibilities. x is 0 or lambda is 1. Let's look at two cases separately. The first case, if x equals to 0, then what does equation 2 and equation 3 tell us? Then equation 3 gives y squared equals to 1. That means y could be plus or minus 1. So we get 2 points from this equation. First point, when x equals to 0, y equals to positive 1. And second point, when x equals to 0 and y equals to negative 1. How about the second case? If lambda equals to 1, then equation 2 becomes 4y equals to 2y. This equation is consistent if and only if y equals to 0. And if y equals to 0, we substitute that to equation 3, then we get x squared equals to 1. That means x equals to plus or minus 1. Then we also get 2 points from these two equations. First point, when x is positive 1 and y is 0. And the second point, when x is negative 1 and y is 0. Then we can substitute these 4 points back to our original function f of x and y and find the value of the function to determine which is the maximum and which is the minimum. So we have f of 0 and 1. This equals 0 squared plus 2 times y squared, that equals to 2. Similarly with f of 0 and negative 1. The value at this point is also 2. Then the other 2 points, f of 1 and 0. Then the function is 1 squared plus 2 times 0 squared. So the value of f at this point is 1. And the last point, f of negative 1 and 0. We will also get positive 1 since we have the x squared in the function. Now we get to our 4 points with the value of the function. The first 2 points would give us the maximum of the function, and the last 2 points would give us the minimum of the function, given the constraint x squared plus y squared equals to 1. So the conclusion is, the maximum value of f on the circle x squared plus y squared equals to 1 is f of 0 and plus or minus 1, which equals to 2. And the minimum value of the function is f of plus or minus 1 and 0, which equals to 1. And below it shows the surface of f of x and y, also the circle C that is projected on the surface. So we have this surface that is C equals to x squared plus 2 times y squared. And when this surface is subject to the constraint of this circle x squared plus y squared equals to 1, and we project this circle to the surface, then we get this curve here, the C. And we can see that this curve has 2 maxima and 2 minima. The maximum is at this point, and the other point that is opposite to that point. And these 2 points has coordinates of 0 and 1, and 0 and negative 1. And the point that is opposite to this point will be the minimum, and they are at the coordinates 1 and 0, and negative 1 and 0. And that is the end of the lecture. We could also maximize or minimize a multivariable function given 2 or more constraints. In the next lecture, let's talk about the Lagrange multipliers with 2 constraints.